Okay, let's unpack this. You interact with it every single day.
Yeah.
You literally cannot live without it, yet you probably never really stop to truly think about it.
Not really, no.
We see it in a glass, in the shower, in the rain, and it just seems, well, ordinary.
Mm-hmm.
But that's the paradox, isn't it? It's so ordinary, it almost becomes invisible to our curiosity, yet it's so incredibly essential, it quite literally defines life.
It really does.
So today, our mission for this deep dive is to pull back the curtain on the most common, yet I think, most extraordinary substance on Earth: water.
We're going to explore its hidden complexities, yeah,
Well-
from its molecular magic right through to its role as the absolute bedrock of all life.
It's fascinating, isn't it? We're aiming to go far beyond that common understanding of just liquid stuff.
Exactly, and really explore water's unique molecular structure, the incredible properties that emerge from it, and precisely why this seemingly simple liquid is the absolute bedrock of all life as we know it, right down to the very cells in your body.
So let's start at the absolute beginning. The molecule itself.
Mhm.
We all know the famous HO,
HO.
2 hydrogen atoms, 1 oxygen atom. Sounds so simple,
It does.
but the magic isn't just what atoms are there, but how they interact. What makes this particular trio so special?
Well, what's truly remarkable is how the vastly different natures of hydrogen and oxygen, strong electron pulling power, for instance, create this unique charge distribution that defines water.
Okay.
Oxygen is naturally highly electronegative. It's like a real electron magnet. When it forms covalent bonds with hydrogen, meaning they share those electrons,
Right, they share.
it doesn't share them equally, not at all.
So it's not a perfectly even split then. What does that unequal sharing actually create?
It creates what we call polarity. That stronger pull from oxygen makes its end of the molecule slightly negative, leaving the hydrogen ends slightly positive.
Ah,
Think of it like a tiny, highly specialized magnet with distinct positive and negative poles.
so this magnet effect is crucial. But there's another piece to the puzzle here, isn't there? The actual physical shape of the molecule.
Yes.
Water isn't just a straight line, is it?
No, definitely not. And that bent shape is absolutely fundamental to everything that follows. Water molecules are bent at about 104.5 degrees.
104.5.
Yeah. This V shape is actually caused by the lone pairs of electrons on the oxygen atom, which kind of push the hydrogen atoms downward.
Okay.
And that bend is critical because it dramatically reinforces the polarity. So you have oxygen at the negative apex and the two hydrogens forming the positive base.
So for our listener, if we're imagining this HRO molecule, what does it really look like? Can we picture it?
Okay, yeah. I picture it like a family of three, a strong-willed oxygen parent, and two smaller sort of dependent hydrogen children.
Right.
Oxygen is definitely hogging the toys, the electrons making it feel a bit charged and negative, while the hydrogens are left feeling a bit exposed and positive. And instead of holding hands in a straight line, they're huddled together in a V shape, like a tight hug.
A V-shaped hug. I like that.
Yeah, that bent shape ensures that one side of this tiny family always has a slightly negative charge, and the other side always has a slightly positive charge, just like a microscopic magnet.
And because of that tiny magnet effect, these water families don't just exist alone, do they? They like to hold hands, or rather attract each other.
Precisely. Because of their polarity, water molecules are constantly attracted to one another. The slightly positive hydrogen of one molecule is drawn to the slightly negative oxygen of another.
Okay.
These attractions are called hydrogen bonds. Now, individually, they're relatively weak. Think of it like maybe loosely holding hands in a huge crowd.
Uh-huh.
But collectively, they create this vast interconnected network. And that gives water its truly extraordinary collective properties. These bonds are like the secret to its superpowers.
So this bent, clingy nature isn't just a quirky detail, is it? It's the engine behind water's most extraordinary powers, the ones that literally make life possible.
It truly is. These hydrogen bonds are the key to what we call water's emergent properties. Things that you wouldn't expect just from looking at one molecule alone.
Like what?
Well, first, there's its remarkably high cohesion and surface tension. Water molecules stick to each other with surprising strength. That's cohesion.
Okay, sticking together.
Exactly. And this creates surface tension, which is why water forms those perfectly spherical droplets, or why a tiny water strider can literally walk across the surface of a pond without sinking. It's like a skin on the water.
Wow. I remember as a kid trying to float a paperclip on water and thinking it was pure magic. That's surface tension at play, right?
Absolutely. That's
It's
it.
amazing how a tiny insect can walk on it while a human, well, obviously can't.
Exactly. And water also sticks to other things, which is called adhesion.
Adhesion.
This is why water molecules can actually climb plant stems, defying gravity, all the way up to the highest leaves of, say, a towering redwood tree.
How does that work?
Think of it like a long chain of friends pulling each other up a rope. Water molecules pull other water molecules up, that's the cohesion, and the plant's internal structures provide the rope for them to cling to, that's the adhesion. It's a truly elegant system.
It's incredible how that enables something as massive as a tree to get water to its highest leaves. Okay, then there's water's incredible ability to handle heat.
Indeed, water has a very high heat capacity. It's like a giant thermal sponge.
And a heat sponge.
Yeah, it takes a lot, and I mean a lot, of energy to significantly change water's temperature. You know, you try to boil a kettle of water, and it takes time, right?
Feels like forever sometimes.
Exactly. Compare that to trying to heat a thin piece of metal. Water is incredibly resistant to temperature shifts. This property is vital for stabilizing Earth's climate, preventing extreme temperature swings between day and night, making our planet habitable. And it's also precisely how animals regulate their body temperature. Like when we sweat, every drop of evaporating sweat carries a tremendous amount of heat away from your body, cooling you down.
That makes sense. And then there's ice. It floats. Which sounds so simple, but it's actually incredibly unusual for a frozen substance. Most things get denser when they solidify, right?
They absolutely do. It truly is an anomaly, one of water's most famous quirks. When most substances freeze, their molecules pack closer together, making the solid denser than the liquid.
But not water.
But when water freezes, those hydrogen bonds lock into an open crystal structure. They kind of hold each other at arm's length, creating more space between the molecules. This makes ice less dense than liquid water.
So it's like a winter blanket for lakes and oceans. Keeps everything underneath from freezing solid.
Precisely. And to truly appreciate this, imagine for a moment a world where ice didn't float, where it just sank to the bottom like most other frozen substances. The impact on aquatic ecosystems, on life itself, would be catastrophic. Ponds and oceans would freeze solid from the bottom up every single winter, killing pretty much everything within.
That's a chilling thought.
Instead, that floating layer of ice acts as a thermal blanket, insulating the water below, allowing fish and other organisms to survive the cold season. So yeah, these properties collectively allow water to remain liquid across a wide temperature span, forming the basis for everything from blood and cytoplasm to sap and vast oceans, making Earth the thriving planet we know.
Okay, so if that's what water is, let's play a what-if game. What if water's molecular structure was different? What if those HO molecules were linear, straight, instead of bent?
Oh, that's a great thought experiment. If water's bonds were linear, the molecule wouldn't be polar in the same way. The charges would essentially cancel out.
No distinct positive and negative poles.
Right. And without that specific polarity, you lose hydrogen bonding completely.
And without hydrogen bond?
You lose all of water's unique properties. No high cohesion, no surface tension, no high heat capacity, no wide liquid range, no ice floating, no universal solvent power. Life as we know it would be utterly impossible.
Wow.
That bent shape of water molecules isn't just some random chemical detail. It's truly the shape of life itself.
And what would Earth look like then? Let's imagine a few scenarios. First, Earth without any water at all. Just gone.
Oh, bleak. Without water to regulate climate, days would be scorching hot, nights freezing cold. You'd have extreme, uncontrolled winds sweeping across a barren landscape.
No life chemistry.
None. DNA and proteins rely on water to fold correctly and interact. Without a solvent for essential reactions, all life chemistry would simply stall. Earth would be a barren, brown, and gray rock, basically, much like the moon or Mars, perhaps. No clouds, no rain, just bare crust and craters.
It's hard to even picture. Okay, what if we had some water, but much, much less than we do now? Like, say, only 10% of what we have.
Right. Imagine tiny, isolated oceans, maybe more like large seas, and vast, unforgiving deserts covering most of the planet. The climate would be far harsher, like a global desert.
So life would be.
Life would be severely limited. Small, isolated pockets clinging to existence near rare rivers or maybe underground aquifers. Agriculture would be incredibly difficult, forcing any potential civilizations to cluster only around these meager water sources. if they could even develop at all.
And biodiversity.
Extremely limited. Instead of lush forests and vibrant ecosystems, you'd likely see sparse, maybe uniform life dominating. Evolution itself would probably slow dramatically because there'd be fewer opportunities for new niches to develop.
Okay, and on the flip side, what if Earth had too much water?
Yeah.
If it was just an endless ocean world, no continents.
A water world scenario. Well, if water covered everything, you'd have no land, obviously, so no soil, no land plants.
No fire.
No fire, no metallurgy. Human civilization as we know it, with our tools, agriculture, writing it, likely never develops. Life might still exist, of course. You could have thriving oceanic species, fish, marine invertebrates, maybe even intelligent aquatic life.
But not us.
But certainly not human civilization as we understand it. So if we connect this to the bigger picture, Earth's existence and our own, it really balances on this narrow edge of liquid luck. It's not just having water, but having the right amount.
How much do we actually have?
We have about 1.4 billion cubic kilometers of water, which truly seems to be, well, a perfect sweet spot for the kind of life that evolved here.
It's mind-boggling to think about how finely tuned everything is. Now, scientists sometimes consider alternative life liquids for exoplanets, right? Things like ammonia or methane. How do those stack up against water? Do they really have a chance?
It's a fascinating area of astrobiology. Well, let's take ammonia in natures. It is polar like water, and it can dissolve some substances.
Okay, so that's promising.
Sort of. But its liquid range is much narrower than water's, and crucially, it requires extremely cold temperatures to remain liquid. Think temperatures far below freezing on Earth. It's like a less effective, much colder cousin to water.
And methane, like on Titan.
Methane, CH, which we see lakes of on Saturn's moon Titan, is non-polar. That's a huge problem. It makes it a terrible solvent for the complex, charged chemistry that life, as we know it, seems to require. Plus, it also needs ultra-cold conditions, even colder than ammonia.
Any others?
Well, there's formamide. It has a wider liquid range than water, actually, and dissolves organics well. But the issue there is abundance and cycling. It's much rarer than water, and it lacks water's stable cycling through atmosphere, oceans, and land, which seems crucial for a planetary life support system.
And things like liquid hydrogen.
Even more extreme. Incredibly low temperatures, nonpolar, very poor solvents for complex molecules.
So it's fair to say that while scientists quite rightly ponder life as we don't know it using something else, no other liquid really checks all the essential boxes the way water does for life as we do know it.
Precisely. Water's unique combination, that wide liquid range suitable for Earth's temperatures, its polarity and hydrogen bonding making it an unparalleled solvent, its density anomaly where ice floats, and its sheer abundance covering 70% of our planet's surface. It's just a perfectly tuned set of chemical miracles. It's truly a standout in the cosmic chemistry set.
Let's talk more about that unparalleled solvent part. Water is often called the universal solvent. What exactly does that mean? And why is it so powerful at dissolving so many different things?
Yeah, the universal solvent title is a bit of an exaggeration. It doesn't dissolve everything, obviously.
Right, oil.
Exactly. But it dissolves more substances than any other common liquid we know. And this is entirely due, again, to its polarity and that bent shape we discussed.
The tiny magnets again.
Those tiny magnets, yes. Think of each water molecule like one. When you drop, say, table salt, sodium chloride, into water, the slightly negative oxygen ends of the water molecules pull on the positive sodium ions in the salt crystal.
Okay.
And the slightly positive hydrogen ends pull on the negative chloride ions. These tiny magnets effectively swarm the salt crystal, surround the ions, and pull the crystal structure apart. That's dissolving it into solution.
And for other things, like sugar.
For other polar molecules, like sugars or alcohols, water forms hydrogen bonds with them, effectively hugging them and integrating them into the water network, pulling them into solution too.
So water is like a crowd of incredibly friendly people, all with little magnets, tugging apart clumps of Lego bricks maybe, and distributing each piece until everything is spread out and mixed in.
That's a great analogy, actually, and it dissolves an incredible range of substances. Ionic compounds like salts and minerals, many polar molecules like sugars and alcohols, and even gases like oxygen and carbon dioxide.
Oxygen, which is how fish breathe underwater.
Precisely. Or how essential gases cycle through our oceans and blood. What it doesn't dissolve well, like those nonpolar oils and fats, is also really important biologically. Think cell membranes.
And the consequences of this dissolving power are everywhere, right? In nature and society.
Absolutely everywhere. In nature, this solvent power means nutrients dissolve in soil water and get transported up into plants. It means oxygen and sugars dissolve in our bloodstreams, powering every single cell in your body. It also drives the weathering of rocks over geological time, slowly dissolving minerals and creating fertile soil.
And in society.
Oh, countless uses. Cooking relies on dissolving flavors and ingredients. Cleaning uses water to dissolve dirt and grease, often with soaps helping bridge the gap with non-polar stuff. Countless industrial processes, chemical reactions, medical applications, they all depend on water's ability to dissolve things. It's literally the medium through which much of our world's chemistry happens.
But this universal solvent power, as you hinted, can also be a double-edged sword, right?
Yeah.
A gift and maybe a curse?
It absolutely is. Because water dissolves so much so readily, it also easily picks up and carries pollutants.
Ah.
Think of things like heavy metals from industrial waste, pesticides and fertilizers from farms, microplastics shedding from synthetic materials, even pharmaceuticals that pass through our body.
And once they're in the water,
Once these contaminants are dissolved or suspended in water, they can spread everywhere into rivers, lakes, oceans, groundwater, and ultimately, potentially into our drinking water supplies and food chains.
so water acts like the world's most efficient postal system, maybe, but it doesn't check the contents. It just delivers everything.
That's a really good way to put it. It delivers vital nutrients, yes, but it can also deliver dangerous poisons to every corner of the planet and every level of the ecosystem.
And why is this dissolving power so critical for life itself?
Well, without water's dissolving power, life's complex chemistry just wouldn't flow. Cells need dissolved nutrients. Enzymes need a water environment to function. Transporting substances within an organism, removing waste products, it all depends on things being dissolved in water. Complex, evolving life simply wouldn't exist without it. But that very same power demands our vigilance in protecting our water sources from contamination.
This deep dive really makes you look at water differently. Beyond its fundamental role, there are some truly surprising, almost paradoxical facts about this amazing substance that underpin everything we've discussed. We've touched on its anomalies, those weird properties that make it so special.
Yeah, water truly is full of exceptions to what you might consider normal rules for liquids. We talked about its density anomaly, where ice float's absolutely crucial. But also, its expansion when frozen doesn't just save aquatic life, it cracks rocks over time, helping create soil and driving mountain erosion over geological timescale.
I never thought about that connection.
Its high surface tension allows raindrops to form beads, shaping how water interacts with landscapes and soil. Its incredibly high specific heat capacity makes oceans Earth's giant thermostat, preventing wild temperature swings day to night and season to season. And its high heat of vaporization is why sweating is such an effective cooling mechanism for us. Life absolutely depends on these chemical oddities, these rule-breaking traits.
And thinking about how long water has been around is truly mind-bending. It's older than the Earth.
Much of it is, yes. It really makes you stop and think about the journey of every single drop. It's almost poetic, isn't it?
Yeah.
When you hear that most of Earth's water likely formed in interstellar molecular clouds from hydrogen and oxygen created in stars even before our solar system came to be, well, it gives you a completely new perspective on drinking a simple glass of water.
So every
Sip you take has been part of countless cycles over billions of years. Oceans, glaciers, clouds, rivers, passing through organisms. It means that the water you're drinking today could literally have flowed through the bloodstream of a dinosaur, maybe cycled through an ancient rainforest, or been part of a prehistoric ocean. We're truly connected to something vast and ancient every time we drink.
And it's not just around us. It's profoundly in us. You mentioned the percentages earlier.
Indeed, you are about 60% water by weight. Your brain is roughly 75% water, your blood about 83%. Even your bones, which feel so solid, are around 22% water.
Wow.
We don't just need water to survive. We fundamentally are water in many ways. We are, in essence, walking, talking oceans contained in skin, a testament to water's fundamental role in our very biology.
It also seems to be a silent historian, recording the past for us in unexpected ways.
It truly is. Ice cores, for example, are like frozen libraries. Scientists drill deep down into glaciers in Greenland or Antarctica and pull up these cylinders of ice that have trapped tiny bubbles of ancient air.
Trapped air.
Yes, perfectly preserved snapshots of Earth's atmosphere from hundreds of thousands of years ago. They can analyze those bubbles to tell us the exact carbon dioxide levels, methane levels, evidence of volcanic activity, even dust storms from distant continents.
Incredible.
These cores have been been absolutely fundamental in understanding past climate change and putting current changes into context. And similarly, ocean sediments lay down layers over millennia, recording shifting temperatures, ocean currents, and the history of marine life, all mediated by water.
And it transcends science too, doesn't it? It shows up in nearly every culture and religion across the globe.
Oh, absolutely. Water is almost universally used in religious rituals for purification, for baptism signifying rebirth as a blessing. Creation myths across many cultures often begin with water primordial oceans, cosmic floods that reshape the world.
Why do you think that is?
Well, I think we instinctively understand that water is more than just a physical substance. It's essential for life. It cleanses, it flows, it changes form. It's woven into our deepest meanings and stories, symbolizing life, change, purity, and renewal. It really raises an important question. How often do we truly appreciate something so fundamental yet so profound beyond just its practical uses or scientific properties?
And despite its seeming abundance covering so much of the planet, it remains our most fragile dependency. You hear stats like, we can survive about 3 weeks without food, but only about 3 days without water. That's quite sobering to think about.
It is, and it's often the most overlooked dependency until it becomes scarce. In almost any survival situation, finding a safe source of water comes before finding food or even sometimes shelter. It's the immediate, non-negotiable requirement for our continued existence.
So when you really think about it, water isn't just what fills your glass, it's what fills the world, your body, and your story. It feels like asking what is water, is truly asking what is life.
I think that's a beautiful way to put it. It's not just something we drink or a simple H0 molecule. It is the very medium of life itself, absolutely packed with these chemical miracles that we so often take for granted.
To take water for granted is, maybe, to forget the delicate balance of chemistry and physics that makes Earth habitable and our own lives possible.
It's a constant, quiet miracle happening all around us and inside us all the time.
So maybe the next time you drink a glass of water, just pause for a second. You're not just quenching thirst, you're participating in the exact same chemical miracle powered by that bent little molecule and its sticky hydrogen bonds that has sustained life on this planet for billions of years.